Yeah, so hello and welcome, students. So let us start today's class. So MA415 Algebra. Okay, and this is lecture number 29. Okay, so now recall we are discussing about few ideas, and we started with something called the field. The field is a very nice object, and then we prove that you have an object which cover bigger than this field. So every field is that object, and that is called Euclidean domain. We prove it that every field is an Euclidean domain, and also we prove every Euclidean domain is a principal ideal domain, PID, and then yes, 1 minute. UFD, unique factorization. This is PID. UFD, unique factorization domain, and then you have bigger thing, integral domain. Okay, integral domain. In fact, there is something called factorization domain, but that is not so important, so I am not writing. There is something where you can factors, but it's not UFD, and there's something which is ID, but it cannot be factor. So in between there's something called you can also write down FD, factorization domain, and then ID, integral domain, and the general ring. So what does that mean? That means you start with the general ring, and then you know that inside that ring there is a special class of ring, and that is called integral domain. And there is another special class called factorization domain where you can do factors, and then a special class called UFD, unique factorization domain, and there is another special class inside UFD that is called principal ideal domain, and then Euclidean domain, and then field. So field is the most precious nice object. Okay, and these are all proper inequalities. What I mean that there are examples that field is equivalent domain, but there are equivalent domain which is not a field. Like for example, Z ring of integers is equivalent domain is not a field. And then yeah, so maybe I will give an example in each cases. Okay, case 1. So examples 1, ring of integer is an Euclidean domain but not a field, right? First example, why it is not a field? Because you cannot invert every non-zero element, right? Like 2 doesn't have an inverse in Z, right? Now question number the example 2. So this is, you understood this portion. Now this portion, so we already proved that Euclidean domains are principal ideal domain, but the question is that whether every PIDs are ED, and the answer is no. So there are example. For example, Z1 plus root over minus 19 by 2. This is actually something called ring of integers of Q root over minus 19. Okay, it is sitting here as a integral ring of integers of that. So the Q of this is the quotient field of this, a field of fractions. This is field of fraction, okay, of this. Okay, so this will show that this is a PID, but not this ED, Euclidean domain. Okay, I will show it one by one. So let me just and then you have, so something PID not ED, and then maybe example 3, that you have something which is here. So in this case you can find out something UFD but not a PID. And there are several examples, but let me give one example. Say polynomial ring over set is an UFD, unique factorization domain, but not a PID, principal domain. Okay. And then maybe I can give another example here, from here to here. So we can like that minus 5 is FD factor domain, or you can factor but not a unique operation domain. Okay, and so on. I mean, you can find out a domain which is where you cannot even factor. So what do you mean by factors? That when I'm saying factorization domain, I mean it has a finitely many. You can write it down, product of finitely many factors, but they are not irreducible. But this is not unique. That is the meaning. Okay, so you can factors, but the uniqueness property is not there. But there are other domains there you can even you don't have even finite factors. Okay, so for example, if you collect say so let me write down, so maybe say half. Okay, this is all the elements of this form, 2 power n. Okay, and so this is a belongs to z and n belongs to certain number, or 0. N can be 0 also. Okay, so you understood that this contains z itself, but this is not even a FD, because if you start with 2, you can write down 2 into 2 into half, and then you can write down 2 into 2 into 2 into half into half, and so on. So you cannot, sometimes you cannot even stop this kind of factorization, right? Half. So yeah, so some way you can define by this also, this kind of domain where the factorization is a problem. Okay, now the few important thing before we are going to give proof, few important thing I am just going to discuss. One important thing which we already discussed, that I recall that we proved that for a field F, the polynomial ring this is an Euclidean domain. Okay, where for a field. Okay, now the question is that what of the converse? Suppose you have a so the question, I mean, you start with something, say let say RB let me just use commutative unital ring. I mean, commutative is united unital ring such that this is a this is a ED, or maybe less than that, is a PID, principal ideal domain. Then what happened? Then what can you say about R? Like, I just want to know what kind of ring is this. Is integral domain only, or it may have some important mode property. The answer to this question is that then answer. So under that condition, R is so this is a PID if and only if R is a field. That is the answer to that question. Okay. So one part we already proved, if R is a field, then Rx is a ED and hence it is a PID, right? Because we already proved this is a PID, right? So the converse part we need to give proof of the converse part. Okay. So so let Rx be a PID. So what does that mean? That means Rx is also ED, right? ID, integral domain. Then R is an integral domain, right? You can prove that just subring of integral domain is an integral domain. Okay. So R is commutative ring with identity without zero divisors. That is the meaning of integral domain. So now once you have integral domain and when you have integral domain property, then you can obviously you can say many things. Now you see that the ideal generated by indeterminate x, if we start with this, so this ideal is a prime ideal, right? This prime ideal is obvious because if you see that if any two product belongs to that ideal, so yeah, so prime ideal as if fx and gx belongs to ideal generated by x, then what happens? Then you can write down fx into gx equal to say x times hx, okay, and hence x must divide one of so x divides fx or x divides gx, right? So what does that mean? That means either fx is an element of the ideal generated by x or gx is an element of ideal generated by x. Okay, so this is a prime ideal. Okay, and hence this is also maximum ideal because you know that Rx is a PID, hence this is a maximal ideal as Rx is a PID, and we already proved that in principal ideal domain every prime ideal is a maximum ideal, right? So what does that mean? That means that you have this maximum ideals, and if you quotient out by that, so this this R is actually isomorphic to Rx mod x, and we know that this is a field, right? Because if you quotient out by maximum ideal into integral domain, this becomes a field, and this is also isomorphic to R. So what does that mean? That means R is a field. Okay, so this is the proof that whenever you have a polynomial ring which is a pictorial domain, then the original ring must be a field. Okay, so so this is kind of important description one-to-one, but instead of R, suppose if we have a general ring instead of a field, then what about that ring? Like there is Zx, and you recall that we have given the example that Zx is a UFD but not a PID. So UFD means unique factorization domain, and that is almost obvious, right? You can factor any polynomial in terms of small polynomial, right? So ZX, now we will prove that ZX is not a principal ideal domain. Okay, now how do you use this proof of this kind of statement? So it is better to find out a ideal which is not a principal ideal, right? And then you are done. And so let me start with an ideal. So so you start an ideal. So let me write down 2 and x. Okay, be an ideal of Zx. Okay, and we will show that this I is not a principal ideal. Okay, so so this is my claim. What is my claim? Claim is that I is not a principal ideal. Okay, now generally we prove this kind of statement by method of contradiction. So on the contrary, how to prove? On the contrary, let us assume that I is generated by single element, some fx. Okay, for some fx belongs to Gx. Okay, so this is a polynomial over interior coefficients. So what does that mean? That means so this means what? So this ideal generated by 2 and x. This is actually fx, right? So what does that mean? See, first of all, if 2 belongs to so 2 belongs from here, you can easily say that 2 belongs to fx. So this is one condition. If 2 belongs to fx, that means 2 is a multiple of, right, this something, some gx time fx, right? And that automatically tells you that this automatically tells you this implies that so this is a polynomial, this polynomial, and this is 2. So this automatically tells you that this constant polynomial, right? Unless otherwise gx is constant polynomial. So gx is a constant polynomial. Now if gx is a constant polynomial, this implies that then x cannot belong to this ideal generated by a constant, right? So this is a which is a contradiction, right? Which is because we have this, which is a so this is not possible, which is a contradiction. So what does that mean? That means Zx is not a PID. Okay. Now the other examples, some of the examples are very difficult to prove, but maybe I will discuss something so that you have some idea how to prove. For example, this is a PID but not ED. Now to prove this is a PID, it is not a easy thing. Okay, because checking whether every ideal, see, to prove something is not something, then it is easy because you need to find out an example. For example, here 2 is not a special element. You can choose any prime. Okay, so you can choose any prime. Here instead of x also you can choose any some other elements also. Still you can prove that these ideals are not principal ideal. But then this is an example, right? Proper example. But to prove something is a PID, it is not easy because to check every ideal is a principal ideal is sometimes maybe difficult, right? So what does that mean? That means I need some equivalent criteria which will give me a proper way of proving this kind of statement. Okay, so for this purpose we require the idea of something called Dedekind-Hasse norm. Okay, so now let me define what is this, and this is okay. So I hope, okay, let me just See, when I'm saying norm on ring, so what is that? That is a map from a ring R to um, that n union 0 with so this is the meaning of norm. Okay, for me the norm on ring. Okay, not as a field norm. Okay, and in addition, if it satisfies some condition, then we call is a Euclidean norm. Remember your last lecture, Euclidean algorithm. But we can in that condition and define another norm which is less than something weaker than Euclidean norm. Okay, and what is the condition? The condition is that this is a map, obviously satisfy this condition. The second condition is that and also I need some positive condition. So n of a not equal to 0 if a not equal to 0. So this is positive norm. Okay, so only 0 goes to 0, and for all non-zero a and b belongs to the ring R, what happen? Either there are two possibilities, either A and belongs to the ideal generated by B, or what happen? Or there exists some element x belongs to the ideal generated by these two with the property that with this norm, the Dedekind norm of x is strictly less than Dedekind norm of b. Okay, this is a definition. Okay, so what I'm saying, I'm saying that so a positive norm is said to be Dedekind norm if for any two elements, if you choose any two element in the ring which is non-zero element, then one must be belongs to the other of ideal, or if they don't belong, then if you take the ideal generated by both those things, then you must find an element whose norm or Dedekind norm is less than this. Okay, this is the Dedekind norm, so this norm. Okay, so that is what that is you can find out. So you can write x equal to something like SA minus TB. This is an element of this ring. Okay, and norm of SA minus TB. Why I am writing this minus, you will understand immediately after 1 minute. This norm less than norm B. This is the meaning of this statement. Okay. Now I am writing this minus thing because I would like to show that this what is that Euclidean norm is a stronger notation, right? So every Euclidean norm is also a Dedekind norm. Okay, so what does that mean? That means that you can always find out this property for Euclidean norm. Why? Because this is a simple thing, because for Euclidean norm you know that given a and b not 0, then you can write down this is of the form say qb plus r, with r is either 0 or that Euclidean norm, maybe let me write down NE is Euclidean norm of that. The Euclidean norm itself becomes the Dedekind norm in this case. Norm of R is strictly less than this, right? That norm of B, right? What does that mean? That means this A minus QB equal to R, right? So this is the element which belongs to the ideal generated by A and B, right? This element has norm less than B, right? This is I am asking. So then you choose the S equal to 1 and T equal to Q. Then this Euclidean norm implies Dedekind norm, the H norm. Okay. So what does that mean? That means that Dedekind norms are weaker than Euclidean norm. Okay. Now we will prove equivalent statement that will show that existence of equivalent norm tells you about Euclidean domain. Similarly, existence of Dedekind as a norm will tell about something called principal ideal domain. So this is very important theorem. So let R be an integral domain, then R is a principal ideal domain if and only if R possesses a Dedekind has a norm. Dedekind has a norm. I mean, if it has only one, then we have done. It may have more than one also, so we don't care. Okay, so Dedekind has a norm is what? It's a positive norm satisfy this Dedekind has a property. Okay, so proof. See, there are two parts of the proof. So we'll which one we should prove first? So let me prove. Assume that let R be a PID, principal ideal domain. Then actually we can say more. Actually, not only Dedekind has a norm, we have Dedekind has a norm which has multiplicative property. More than that, we can say that. Okay. Now so if R is a principal ideal domain, then what you can do? Then you can define a norm. So now define a map, say n from R to this natural number union 0 by how to define? So you define, first of all, you send the 0 to 0 and then all the units. See, this is clear. I hope you have understood that when the way you define Euclidean norm, the units have norm 1, right? So here also you define equal to 1 for all units in R. Okay, and if it is non-unit, then what you can do? Then we know that principal ideal domains are UFD, right? Unique factorization domain, and hence you can write down that elements, say element that A in terms of P1, P2, and dot P, say K, and this is a product of irreducible irreducibles, and define the norm of A as a 2 power n, 2 power k, that k. Okay, so if I define by that, you can easily prove that obviously this is a map, non-zero map, so non-zero norm, and you can prove that it has this property also. If you multiply by 2 elements and take the norm, this is the product of single norms, right? Because from this, so if we have P1, P2, Pk, and V equal to Q1, Q2, Ql, then product will be P1, P2, Pk, Q1, Q2, Ql, and which is nothing but that, right? So you can easily find out this norm, right? Because see, so I hope this is clear to you. So n of B will be n of A will be K, n of B will be L. Say this M into L, and then if you multiply these two things, it will have K plus L, which is okay. So let me write down. Then you will have, suppose B equal to some Q1, Q2, Ql. Then here you can have in this side this 2 to the power K plus L, which is exactly 2 power K into 2 power L, right? So understood, this property is satisfied. Okay, and not only that, now we can check that this is also a Dedekind has a norm. And now what does that mean? So either, so let you choose 2 elements. So let choose A and B, 2 non-zero element, belongs to R such that what you can do, you can say that A belongs to the ideal generator R B, then you are done. So assume that A does not belong to the ideal generator B, right? If A belongs to the ideal generator B, then that ends the proof, right? Such that it does not belongs to R, right? So now consider the I, which is ideal generated by AB, which is obviously an inside R. Okay. So as R is a PID, I can written as something, say for some R belongs to R, right? Because every ideal generated by a single element, right? So what are the options here now? The options are that so this A B is nothing but ideal generated by R, right? So now so now this implies that B belongs to this ideal generated by R, right? This implies what does that mean? That means B equal to some R1 times R, right? For some R1 belongs to R. Okay. Now question is that can B1 equal to unit? Now note that sorry, R1 cannot be a unit, as then R you can write down as R1 inverse into B belongs to ideal generated by B, right? And this implies the ideal generated by R, which is ideal generated by AB, which will be subfield of B, and this implies A belongs to B, which is a contradiction, because I assume that it does not belong to B, right? Contradiction, as it does not belong to the ideal of B, right? So what does that mean? That means R1 cannot be a unit, right? Now if R1 cannot be a unit, then what happened? Then the way I define the norm, then in norm of R1, then this norm of R1 is bigger than 1, right? Is to do something, right? And it cannot be unit. So thus norm of B equal to norm of R1 into R, which is equal to norm of R1 into norm of R, but this is bigger than 1. So what does that mean? That means norm of B is bigger than norm of R. Done. This is what we want, right? As R is an element of, so R belongs to this ideal generated by AB, so we get an element whose norm is less than norm of B. So thus R has a dedicand has a norm. Okay, now converse part you need to prove. Converse part is more easy. So converse part what you need to prove? Suppose R has a dedicand as a norm, then R is a PID. Now conversely let R has a dedicand as a norm. So if R as a dedicand has a norm, then we need to prove that R is a PID. So you need to start with the in general idea. Let I be any ideal in R. Okay, we will show that any ideal is generated by a single element. Okay, now you write down S is that element norm of A and whatever such that A belongs to I, right? You find out all the because R as a Dedekind has a norm, right? So you know that this is not these are um, so A belongs to I minus 0. So this is positive norm. So you choose every non-zero element and take this thing, right? So this is a substitute method number. Okay. So using well ordering principle, well ordering principle, we have a least element, right? We have a B belongs to I minus 0 non-zero element with minimum norm, right? Or least element, right? Whatever minimum norm. So what does that mean? That means norm of B, that is norm of B is less than norm of A for all A belongs to I minus 0. Only 0 can have norm 0. Okay. So this is the condition we get. Now I will claim that this B is the generator of I. So this is my claim. Claim I is actually generated by this. This is my claim. So how to prove this kind of claim? So I need to start with any element and so that this is a multiple of B, right? Then I am done. So let A belongs to I be any arbitrary element. So this is my, I need to prove this thing. Okay, so I don't know such that, so I'm assuming that so okay, so one minute. So so either I can so the Dedekind norm tells me that okay, maybe I can write down such that A does not belongs to B. Okay, then the property of Dedekind has a norm implies, what does it implies? Implies that there exist A's and T belongs to R with this SA minus TB is element of obviously this element of this ideal generated by AB. Not only that, norm of which is obviously inside I because your A is inside I, B is inside I, and norm of SA minus TB is less than norm of B, right? But again, this is a contradiction because norm of B is the minimum one. See, norm of B is the minimum norm, right? So this is contradiction. Okay, so you cannot have an element inside the ideal generated by AB having norm less than norm of B, right? So what does that mean? That means what I assume is not true. So thus A is inside the ideal generated by B, right? So what does that mean? That means every element is a, so thus every element of I is element inside this, right? And also we know this is this because B is element of I, so thus I is generated by the single element. Okay, so what does that mean? That means R is a principal ideal domain. This is the proof of the main theorem that existence of Dedekind as a norm is a equivalent condition of saying something of is a PID, and this is very important to prove whatever I just said, that z of this is PID. Okay, but the proof is not so easy. So maybe we will just give you the hints. So statement that z of 1 plus minus 19 by 2. So this actually is a PID. Okay, now how to prove? So you need to find out the Dedekind has a norm, then you are done. So now but this is not easy to check, but it's known actually. So define this norm by from this to our natural setup by you say what are the element of this ring. So the element of this ring is of this form: a plus b root over 1 minus 19 1 yeah, so no, 1 a plus b and then 1 plus 2 minus 19 by 2. These are the element, right? And you send it to a square plus ab plus b square. This is a classical work. Okay, so people already know this thing. Now you check that this is a Dedekind as a norm, and the proof is not simple. The proof is also it is a lengthy proof, but you can find out any standard book. Okay, so this is a Dedekind as a norm, and that tells you that this is a PID, because we just proved that every PID something is PID if and only if it has a Dedekind as a norm, right? Well, so this is one part which what we want to discuss. Another part I would like to discuss. Well, let's see how much time I have. So let's see. Yeah, so maybe I cannot discuss a big theorem, but maybe I can discuss like a small thing what we discussed yesterday, that or in the last class, that so inside z this minus 5 in this 3 is so 3 is not a prime. We prove it, right? Already 3 is an irreducible element, but not a prime element, right? So this part we already proved. For irreducible part, obviously there is a bigger proof, like you write down separate element, product of two things, and do all those things. Or what you can do, you just use that that field theoretic norm which is coming from the field of fractions. So this is it to a minus 5, right? So this is sitting inside the field of fractions, which is q of root over minus 5. Okay, field of fraction of these, and here you have the filtering norms, that norm of a plus b root 5 that goes to a square. See, this is minus or minus, so plus 5b square. So this is just multiplicatory filtering norm. See, this is not a obviously Euclidean norm. This is not Euclidean norm. You can, in fact, it's not even Dedekind as a norm. Okay, so using that, you can easily find out that it is not possible. In fact, whenever you have a unit element, so you have the norm of that. Norm of any element is always 1. So how to prove it's not? It is irreducible. So let you can write down 3 equal to say a into b. Okay, so where a equal to a1 plus a2 root 2 minus 5, and b equal to b1 plus b2 to minus 5, right? Because you see that this is element of this form, right? And now obviously you can take norm, this norm both side, and then you will have norm of a into norm of b. Okay, and this will be, this is what by definition this norm is 9, right? Because 3 means 3 plus 0 into 2 to the power minus b, so 3 square plus 0 square is 9, and this will be norm of a and norm of b. What does that mean? That means, see, if norm a or norm b equal to 1, then we are done, right? Then we are done. Why? Because then either a equal to unit or b equal to unit, and that is done, right? That is the meaning of 3 is irreducible, right? If you multiply by, if you can write down by this thing, then one of them is a unit, right? If not, then what happened? Done. If not, so then what are the options? And then if not, then what happened? Then norm of a and norm of b both has to be equal to 3, right? But can it be? Can there be an element of the form that norm of this is a 3? So this is the question. Is this possible? So a1 plus a2, say root minus 5. Is this possible? So this is not possible, right? This is, see, if you can write down by this, then you can have a1 minus 3 that whole square, okay, equal to this equal to a2 square minus 5a2 square, right? And now you just simplify the equation, and you see that this is not possible. Actually, this is not possible. There does not exist any integer a1 a2 such that this is true. So there does not have any element of norm this. Okay, clear? So yeah, so norm, sorry, yeah, no, I have a mistake. Yes, this is norm of, right? So I should say that this is not right. So yes, the norm of a is what? So this is a1 square plus 5 a2 square, that is equal to 3. Yeah, now, yeah, this is right equation. You can norm of a equal to a1 plus a2 into root over minus 5, and norm of that equal to this. Okay, and this is equal to norm of a equal to 3. Okay, norm of a equal to 3, norm of b equal to 3, and norm of a equal to 3 means this is equal to 3, but this is not possible, right? It is impossible. You understood why this is impossible? Because you see, this is all square, right? So see, what are the options? See, if a1 equal to 1 even, then it is bigger than 3, right? So it has to be 0. So this implies a2 has to be 0, right? But then what happens? Then a1 square equal to 3 is also not possible, right? Possible as a1 is element of integer, right? So this is not possible. So you just show that 3 is not an irreducible element, but which is not a prime. That we already proved that this is not a prime, right? Because 3 is nothing but 1. 3 divides 6, which is nothing but 1 plus root over minus 5 into 1 minus root over minus 5, right? But 3 does not divide any of those things. So 3 is not a prime. 3 is not a prime number, a prime element, but 3 is an irreducible element. Okay. Yeah, so with that I will stop today's lectures, but maybe I will continue a little bit more with examples so that you will have more clarity in this subject. Okay, so this is the end of today's lecture.